We describe electromagnetic radiation traveling as waves. There's actually two ways we describe it, either as waves or as photons, as packets of light. But for the purposes of this talk, we'll consider electromagnetic radiation as waves. So that's not the only kind of waves out there. There are also a lot of other types of waves. The thing that's unique about electromagnetic radiation is that it can travel through space. So some examples of that would be like visible light, like the light that we see from the sun. X-rays can also travel through space, and radio and TV waves can travel through space. So radio and TV broadcasts that we're putting out now are currently traveling through space through our solar system. There are other types of waves, but they require some sort of medium, some sort of thing to travel through besides space, besides the vacuum of space. They might require air or the earth or water in which to travel through. And some examples of these would be sound, which requires the air to travel through, or other solids. Seismic waves travel through the earth. That would be another example of waves, or even waves in the ocean. Because all of these things are waves, whether they're electromagnetic waves or not, we can describe some basic wave characteristics. When we talk about these different wave characteristics, one thing that we talk about is the wavelength. And the wavelength measures the distance, as a distance measurement from the top of one wave crest to the top of the next wave crest. That would be the wavelength. Or we could also measure from the bottom, from one wave trough to the next wave trough. That should be the same wavelength. Another thing that we measure is how high the wave goes up and down. This would be a measure of the amplitude of the wave. So you can see in this example here, we're measuring from the wave crest to this inflection point between the wave crest and the wave trough. This wave down here, these two waves, if we compare them, they have similar amplitudes. They both go about the same distance above the zero line here, but this obviously has a much shorter wavelength. If the wavelength is shorter, another way to describe that is it has a higher frequency. So the higher frequency would mean that there's more wavelengths within the same distance. Another way of thinking of that is the wave period. That would be how many waves pass by a particular location within a given amount of time. So here we have a high frequency, short wavelength. Here we have a long wavelength, low frequency. One other thing that we sometimes talk about with waves is whether or not two waves are in phase with each other. And in phase just means that their high points, their peaks, and their troughs line up with each other. In this example here, we would say these two waves are out of phase because their peaks and troughs do not line up with each other. With electromagnetic radiation, like light and X-rays and gamma rays, we can look at that same wavelength, and we can also consider that we think of these things as electromagnetic fields. The electromagnetic field just basically means that if we're looking at the wavelength, there's a wavelength in the electric portion of the field and the magnetic portion of the field, and those two fields are at right angles to each other. But I think much more important to think about here is the wavelength, because we don't really talk about this separation that much in this class. But what we do talk is about the electromagnetic spectrum. So the electromagnetic spectrum is just the frequency or the changing wavelength of the electromagnetic radiation that's arriving to the Earth from the sun or other places in space. And this can vary from very short wavelengths to much longer wavelengths. The visible portion of the electromagnetic spectrum is shown in the middle here. And as we move towards a shorter wavelengths, we get into ultraviolet light, we get into X-rays, and then lastly into gamma rays. These high frequency waves tend to have more energy associated with them, and they can be the dangerous ones, right? We want to stay away from X-rays, and gamma rays come in from space, but not really enough to affect us very much. On the other side of the electromagnetic spectrum, we get longer wavelengths and lower energy. So these lower energy ones don't affect us as much. Radio waves just kind of go right around us. Microwaves, it's fine to have a microwave oven in your kitchen. And infrared is not as harmful to humans as the ultraviolet light from the sun. So So we can kind of think that there's this whole spectrum, right? This whole kind of change in frequency or change in wavelength of the electromagnetic field as we move across here. And that's what's influencing the color of the light we see, or even what type of radiation it is, what type of electromagnetic radiation it is. This shows the same thing, just kind of showing the different wavelengths coming in this direction here. We can see that the frequency is increasing as we move from radio waves to microwaves to infrared light to visible light to ultraviolet light to X-rays and finally to gamma rays. Once again, the energy is increasing in this direction here. That's what makes these dangerous. And the wavelength is getting longer and longer as we move towards the radio waves.